Okay, last class we learned about shapes, molecular shapes, electron geometry shapes, bunch of shapes. We learned 5 shapes. Our simplest shape, if you've got 2 things attached to your central molecule. So we've got our center atom. Our center atom here is carbon. We've got 2 things attached to it. Those 2 things, these 2 electron groups, are negatively charged. Opposites repel each other, and so they're going to spread out as much as possible, which is on complete opposite sides. And so this is going to have a linear geometry. The whole thing will be just a straight line. If we add one more thing to that, then we get this trigonal planar shape. So we've got our carbon in the middle, and we've got 3 things attached to it. 3 electron groups, the furthest they can get away from each other, is in this 120 degree-ish spacing. Trigonal because it's got 3 things. Planar because it's flat as a board. And if we add one more thing, then that's our tetrahedral geometry, where we've got 4 things attached, and this is best demonstrated by hitting an X-shaped pose and then turning the torso 90 degrees. And that's like my hands and feet are each one of the groups. I think that hitting the poses is helpful for learning them. It's also just fun. So I encourage you to do it when you're studying. I'll get a little brain flow into your blood, which is always good. I could probably use some of that. Then we added on a little twist. So we can also have lone pairs as one of our electron groups. And when a lone pair is one of our electron groups, then the shape that our electrons make, our electron groups make, is one shape. That's our electron geometry. So if we've got 4 groups, it's going to be tetrahedral. And if we've got one of those as a lone pair, the lone pair doesn't really take up space in the same way that atoms do, because atoms have their really dense nucleus at the center. And so one of those, boom, disappears. So you make the shape for the electron geometry, you get rid of one of them, because we've got one lone pair, and boom, now we've got 3 pairs, so it's trigonal, and they're not a diva. One of them is bent out of the plane, or all 3 of them are bent out of the plane, rather. And so it's this trigonal pyramidal shape. So it's a pyramid instead of a flat plane. And we can also have a bent shape where we've got 2 lone pairs, and those 2 lone pairs are forcing the atoms out of the linear shape so that they're bent instead. And we could also get that with this shape here, so where we've got a trigonal planar electron geometry and then a bent molecular geometry. And this is a table from our online book that's a summary of all the different shapes. There's more shapes than this. These are just the shapes that we learn. So you can get shapes all the way up to having like 6 things on your central atom, which gets really fun and exciting. And you can also have shapes where you're talking about like multiple centers, which is also really fun and exciting, but we'll save that fun and excitement for a later class, like semesters from now. So the way that you read this is the number of electron groups on the central atom. So this is lone pairs plus any number of bonds. So a single bond, a double bond, a triple bond all count as one electron group. These are the numbers over here. And then we separate them by number of bonding groups. Bonding groups being single, double, or triple bonds. They all count as 1. So if we've got this number of bonding groups and then this number of lone pairs, these are the electron geometries, and these are the molecular shapes. You've got a maximum of 5 different options for your molecular shape. Our electron geometry is simpler. We only have 3 possible options. So the way that we predict geometry using our valence shell electron pair repulsion theory, that's the VSEPR, or Vsepar theory, is our first step. We need to draw a correct Lewis structure for the molecule. So this is what I've been talking about. We're building and building and building. This is some of that building. So we have to be able to draw a correct Lewis structure for the molecule, which contains several steps. Once we've got our correct Lewis structure for the molecule, everything's got its octets, all of our electrons are placed, then we can count up the total number of electron groups around the central atom. Electron groups is anything that's got electrons in it. So lone pairs and single, double, triple bonds. Those are our 4 options for things that constitute an electron group. We can figure out the number of bonding groups, the number of lone pairs. You can kind of do steps 2 and 3 simultaneously. And then you either refer to the table to determine the electron geometry and the molecular geometry, or you visually, in your head, imagine it, or you jump up and you hit the poses and you figure out what's what. And the goal, because it's valence shell electron pair repulsion theory, we're trying to get our electron groups as spread as possible. Okay, so we want to predict some geometries using valence shell electron pair repulsion theory. Spreading out our electron groups, we want the approximate shape of each of our molecules. So our first step would be to draw a correct Lewis structure. For PCl3, we're going to have phosphorus in the middle because we've got 1 phosphorus, we've got 3 chlorines. The chlorines it makes sense to put around the outside. There's other reasons that makes sense as well, so we're going to spread those out. Phosphorus has 5 electrons, and we've got chlorine, we've got 3 of them with 7 valence electrons each, because they're halogens. They're in the 17 or 7A group. So we've got a total of 26 valence electrons. To get everything connected, we need 3 bonds. 3 bonds is 6 bonding electrons, which leaves us with 20 remaining electrons. At this point, we want to place our electrons starting from the outside, the terminal groups, our chlorines, and then working our way in. So we're going to distribute as many as we can to the outside to our chlorines, and then anything else that's left over will go on our phosphorus, and then we'll check our lone pairs. So each of these chlorines has 1 bond, which is 2 electrons. How many electrons do we need to get them up to?
6 more.
We need 6 more to get them up to 8. So we can add 6 to each of our 3 chlorines. 6 times 3 is 18. So 18 electrons to our chlorines. That's going to leave us with 2 left over. And we can put those 2 on our phosphorus. And then if we go around and look at our octets, our chlorines each have their 3 lone pairs and 1 bond. That's 8 electrons. So they've got octets. And our phosphorus has the opposite case. It's got 3 bonds and 1 lone pair, which is also 8 electrons. Step 1, done. Okay, now we want to look, for step 2, we want to look at our central atom. What's our central atom? Phosphorus, P. Phosphorus has how many groups on it? How many electron groups? How many distinct clusters of electrons?
3.
It's not 3. It's not 8. 4. It's 4 because we've got 3 bonds and 1 lone pair. So it has 4 electron groups. those 4 electron groups are broken up into 3 bonds in 1 lone pair. So if we've got 4 electron groups, our shape for 4, hit the X and twist. All right, that's our 4. That's our electron geometry. If we get rid of one of those groups, now we've got 3 groups left. So it's 3 for trigonal. And it's not flat in the plane. It's bent out a little bit because of this electron group, the lone pair, that's causing them to deflect out of the plane, out of being flat. And so this is going to be trigonal because of 3 groups, pyramidal because it's not flat. Shape here is referring to molecular geometry instead of electron geometry. Although it's often helpful to think about the electron geometry to help you get to the molecular geometry. Questions about that? We could also peek back at our table. So we had this case for our PCl3. For our number of electron groups on our central atom, it's 4. We had 3 bonding groups and 1 lone pair. That's going to give us tetrahedral electron geometry and trigonal pyramidal molecular shape or molecular geometry. So you could also refer to the table. And then NOF, nitrogen is the central atom. So nitrogen in the middle, oxygen, and fluorine on the other side. It might be tempting to look at this and say, it's going to be linear because we wrote them out in a line. That's not necessarily the case, although it certainly could happen. So to figure out, we've got to do our Lewis structure. So we've got nitrogen, which has 5 valence electrons. Oxygen has 6 valence electrons. Fluorine's got 7 valence electrons because of the groups that they're in on the periodic table. 5A, 6A, 7A respectively, or 15, 16, 17. So we add those all up and we get 7 plus 6 is 13 plus 5 more is 18 valence electrons. To get everything connected, we have to put some bonds in. We're not going to put a line around to make a little triangle because what do triangles do? Explode. So we're not going to do that. So we just have 2 bonds that we're putting in, so a minimum of 4 bonding electrons. Because we had 2 bonds with 2 electrons each. Okay, so that leaves us with 14 remaining electrons. We can place these starting from the outside groups, our oxygen and our fluorine, and then anything that's left over, if we have anything left over, goes on the nitrogen. So our fluorine and our oxygen each currently only have 1 bond, which means they have 2 electrons. They need to get up to 8, so we can add 6 to each. So we're going to add 3 lone pairs. To get them up to their octets. So that's 12 electrons to our oxygen and our fluorine, which means we've got 2 left to place, and those 2 left will go to the nitrogen. And then all of our pieces are on the board. What we have to do now is check our octets. So we placed 2, 4, 6 electrons on our oxygen, plus 2 more is 8 because of the bond. Our fluorine also has 2, 4, 6, 8. So it's good. Our nitrogen has 2, 4, 6. So our nitrogen only has, sadly, it needs 2 more. It only has 6. So we need to get 2 more from somewhere. Where can we get those 2 more from? Yes?
You can put a double bond with one of them.
Double bond with one of them. That is correct. And so we're going to put in a double bond. And our structure, if I can grab the correct things and only the correct things. Okay. So it'll end up being this for our structure. If you put it on the other side, or if you did like a resonance structure thing, that would also be fine. We don't actually really care about the Lewis structure that much. We're just using it to get to our shape. But I'll show that other option as well. So that would be the other thing that you might get. We don't have the tools to say which of those is correct. One of them is correct, the other is wrong. Okay, so now that we've got this, let's look at our central atom. What's our central atom? Central atom is nitrogen. How many groups does it have? How many electron groups does it have on it? How many separate clusters of electrons? 3. So a double bond is 4 electrons, but they're all in one group, so it counts as one group. So double bonds count as one group. Triple bonds also count as one group. So it has 3 electron groups. How many bonds, how many bonding groups does it have? 2 bonding groups, because a double bond also counts as one in this case. So it's got 2 bonding groups. And how many lone pairs does it have?
1.
1 lone pair. Okay, so it's got 1 lone pair, 2 bonding groups. Let's go refer to our table. So we are looking for 3 electron groups on our central atom with 2 bonding groups and 1 lone pair. So we're going to be in this line. This is our NOF. So our electron geometry would be trigonal planar. That's the YMCA shape with your feet together. And then the molecular shape is going to be bent. So if we get rid of one of the groups, I can't get rid of my legs because I like walking. And also I'm not very good at levitating still. I've been practicing, it's just not coming through. Keep falling over. So our shape is going to be bent. Questions about either of those examples, processes? Confusion's also welcome. Yes?
Do we have to memorize that chart, or will we have like access to it, or the names?
Historically, I've provided that table on the exam for which this material occurs the first time. If it shows up again on the final, you won't have it. But you also need to know like what counts as a bonding group. So like don't get tripped up and think a double bond is 2 groups, because it's just 1 group. Don't think a triple bond's 3 groups, etc. That's kind of like the one thing. So know how to read the table. There's some practice examples once the homework goes up for that. Other questions? I think the table's fun because I'm weird, So like I think learning the shapes is cool, but if you don't think that they're cool, then that's fine. Just learn how to read the table for now. Yes?
So that's going to be on the exam on Monday.
This could be on the exam on Monday.
Could be?
Could be. It's fair game for the exam. I haven't decided if I'm going to put it on there or not yet.
Oh, okay.
I could decide it's too much and I'm not going to put it on.
Let's decide that.
We just won't know until we get the exam?
You either won't know until you get the exam or until I send an announcement and say, here's what I'm including.
Okay.
Yeah. So definitely study up on chapters 5 and 6. And then
All of 5 or the last
all of
5 we did?
5. I think it was all of 5. So you should know how to do it anyway. So 5 and 6. And then this stuff. If there's an area that you're going to prioritize, like put at your lowest priority, it would be the most recent material because that's the stuff that I would cut if I cut something. Again, not guaranteed. I will make no estimations about probability. Okay. Please predict the molecular geometry of the SO3 2- ion. This is for you to practice. If you've got questions along the way, feel free to ask, chat with your neighbor, discuss, refer to the table, etc. Okay. Bless you. If you're stuck on the Lewis structure part, here's the Lewis structure. Didn't like that bracket. Didn't like that bracket either. That's much better. Okay. That's the Lewis structure for the, you should know the name of this ion, SO3 2-. So if you were stuck there, congratulations, you're unstuck. And now you can come up with molecular geometry. Okay, how many bonds do we have? How many groups do we have? How many electron groups do we have on our sulfur? 4. 4 electron groups on sulfur. How many bonds? How many bonding groups? 3 bonding groups. So we've got 3 bonding groups. That means that we must have 1 lone pair. So what would our molecular geometry be for this shape? Our electron geometry would be tetrahedral. And then we get rid of one of the groups, and now it's 3 groups that are showing. So it's trigonal. They're not flat, so it would be trigonal pyramidal. Questions? Okay, remember where I said that we were going to build and then build and then build and then build? We're getting to that. I jumped ahead a slide. So there's also another notation. So we've seen just these straight lines, these single, very simple lines. There's other ways that we can represent molecular geometry and 3-dimensional things on 2-dimensional paper. I don't have any 3-dimensional paper, otherwise I'd show you how we do it on 3-dimensional paper, but on 2-dimensional paper we can use straight lines. So this is for things that are in the plane of the board. And then we've got hashed lines and wedged lines. Sometimes you'll see hashed lines instead as an empty wedge. I usually used just an empty wedge to represent the same thing as a hashed line because I didn't like trying to get all the spacing of the little lines correct and making it look nice. So if we wanted to draw the shapes in 3 dimensions, these are a couple of ways that we could draw them. So A here is representing our central atom, and then X is representing just any other atom group. E is representing a lone pair. And the way that these hash lines and wedge lines work is hash lines are going away from you. These straight lines are in the plane or on the board. On the board. And then the wedged lines are coming out, coming towards you. There are several pieces of food that come in wedges. Who can name a piece of food that has a wedge shape? Pizza. Do we like pizza? Yes, generally people like pizza. I personally enjoy pizza. So if this wedge line represents a slice of pizza, I would like to be eating the slice of pizza. The other thing that it represents that I like arguably even more is potato wedges. And I want to eat potato wedges, and so those are coming towards me. So those are a couple of ways that you could possibly remember those, like pizza, yummy, or potato wedges. So for example, in this trigonal planar example, we've got the x on the left. This one is flat. We've got this x with the wedge line and this x with the dashed or hashed line. And so those are going out kind of like this relative to the board. So the wedged line is this one coming out towards you. The hashed line is this one that's going away from you, would be projecting to the outside of the classroom or into the board. And these are just one way that you can represent these. You can kind of like shift them around 3 dimensions however you want them to work out, just as long as it makes sense. We won't really be doing much with this, if anything. It's kind of just so that you know and you don't get confused in case you see it. This is what these things mean. Okay, building. If you combine oil and water in a container, they will separate into distinct regions. You will get the water down below, you'll get the oil up top. There's something about the water and the oil that causes them to separate out. You shake them up, they separate out. You shake them up, they separate out. You shake them up, they separate out, right? It just will do that no matter how many times you try to get them to stick together. In water, which has this formula, this Lewis structure, the oxygen and the hydrogen atoms each donated 1 electron. So hydrogen put its 1 electron in, oxygen put an electron in, and the same thing on the other side. So they each contributed 1 electron. However, they are not sharing these electrons equally. So in these bonds, oxygen is actually hoarding the electrons. The electrons, if we were to look at a projection where the electrons are found, we would see that the electrons are found closer to the oxygen in the middle. And the hydrogens are kind of left out there with less than their fair share of electrons. And this is because of the electronegativity. So oxygen is more electronegative than hydrogen. It pulls electrons better than hydrogen. So a lot of electronegativity, I like to think of it as like a tug of war, and electronegativity is our pulling stat. So the higher your electronegativity value, the stronger that you are at pulling, and the more likely you are to win at keeping that electron close to you in the tug of war. So our electronegativity is the ability to attract electrons within a covalent bond. It uses a relative scale, we arbitrarily set 4 as the highest value. And fluorine is the only element with a value of 4. I will often be abbreviating electronegativity as EN because I don't like writing all those letters. If you have your yellow sheet has all the electronegativity values on it. So you should, if you look at fluorine, you'll find in that box of 4.0. That 4.0 is where the electronegativity is going to be found for all of the other squares. So for example, on oxygen, you'll see a 3.5. I think chlorine's a 3.1, carbon's a 2.1, somewhere in thereabouts. You don't need to know, you don't need to like have all of the electronegativity values memorized. If you're going to memorize one, it should be fluorine. Fluorine has a 4, a 4.0, perfect GPA. Fluorine's going to college for pulling electrons, surprisingly. Okay, so the way that the electronegativity works out in these bonds, because of the unequal sharing, the oxygen atom gets a partial negative charge, and we symbolize the partial. I think this is lowercase delta. It's not really that important that it's a music note looking thing. But I think it's lowercase delta. And so we use this to symbolize partial charge. So it's not like the full positive and negative charges that we get in ionic compounds. Like oxygen forms O2 minus when it's an ion. We're not talking about full charges. We're talking about just like somewhere between no charge and 1 charge. Like if it completely stole the electron, that would be 1 charge. The hydrogen atom, because it has less than its fair share of electrons, gets a partial positive charge. And the result of this uneven electron sharing is what we call a dipole moment. What does the di prefix stand for? 2. Where are poles found on the Earth? I'm not talking about a venue, I'm talking about like geography. North and south poles. So like north and south poles on Earth, or more relatably, positive and negative poles on a magnet, or north and south poles on a magnet, because they're sometimes also called that. And then the moment part, I think, comes from physics. So I'm not sure how to explain that to you. But it's a dipole moment. In the moment, we've got a partial positive, a partial negative. Those are our two ends of our little like sort of mini magnet in the bond. So our hydrogen would be on this side. Our oxygen would be on this side. Oxygen's a little bit of a bully. It's stealing the electrons, and so it gets the partial negative. Hydrogen's got a lower electronegativity value, and so it's got a partial positive. We've got a bunch of options for different pairings. So like some of these fights are pretty even. Some of these fights, it's sort of like one team is going to definitely win. Some of these fights are an all-out massacre. You're just stealing the electrons, basically. So those are kind of our three options for the disparity in these battles. You could think of it like if you've ever seen like World's Strongest Man competitors, and then you've seen like a normal person, and you imagine them getting into a tug of war competition, it's pretty clear who's going to win. Or if you get like two normal people from the class, like it might be pretty close. Or if you get like the strongest guy you know at the gym, if you go to the gym, and then like you, if you're not the strongest person at the gym, you know, like there's some disparities there. And this also is happening within our bonds. So covalent bonds, these are the ones where they're sharing electrons, the ones that show up in our Lewis structures. If they have a dipole moment, the partial positive and partial negative, These are called polar covalent bonds. Polar because it has poles. Wow. So it has poles and it's a covalent bond. They are sharing, but it's not even. So it's not equal sharing of the electrons. And there's kind of a continuum of how even or uneven the sharing is. We're going to just generally split things into the three categories I was talking about earlier. It's close, one person's obviously going to win, and somebody's going to die. Those are kind of like the three that we're going to talk about. Okay, I was wrong. Carbon's a 2.5. It's hydrogen that's a 2.1. So for electronegativity, generally speaking, our electronegativity increases towards fluorine. So things that are closer to fluorine tend to have higher values. And then as you move away from fluorine, the values get lower. So like over here on the opposite corner of the periodic table, we've got really low values. They're going to lose in a fight every single time. There's also a mnemonic if you, for some reason, need to know the order. I don't know that it has any value for us, but Fonkel brick ship. I know, isn't it lovely? Fonkel brick ship. That's the electronegativity order of the first however many elements that is. Thank you, undergraduate organic chemistry, for teaching me that one. Okay, so we've talked about where there's like a moderate disparity, a moderate difference in electronegativity. If the two elements, though, have the same electronegativity, or basically the same electronegativity, then the electrons are shared equally or roughly equally, and we're not going to get a dipole moment. No separation of charge. We don't get the partial positive, the partial negative. And we call these non-polar covalent bonds, not having a positive pole, not having a negative pole. It's just pure sharing. Like all of our kindergarten teachers wanted of us, right? Pure sharing of the electrons, equal treatment. Any and every bond between two atoms of the same element is nonpolar. So for example, looking at chlorine bonded to chlorine. So chlorine's bonded to chlorine. Chlorine has an electronegativity value of 3. The other chlorine, since it's also chlorine, has an electronegativity value of 3. If you put them head to head in a fight, there's not going to be a winner. It's a dead standstill. Our difference in electronegativity, 3 minus 3 is 0. Full sharing. So nobody's pulling the electrons stronger towards them. They just get stuck in the middle. What a covalent bond should be. This would be like if you know twins, like identical twins, and they got into a fight. Who knows who won? Even if one person wins, good luck. If you get a very large electronegativity difference, like bigger than the covalent, the polar covalent bonds that we were looking at before, if we get a really large electronegativity difference, the electron is transferred. And the bond is called ionic. Where else have we seen the word ionic? Is it Hyundai? Oh, sorry. Where else have we seen the ionic in the chemistry class? Nomenclature? What kind of things make ionic compounds? A metal and a nonmetal. So this is also a great way to identify something as ionic. If we have a metal bonded to a nonmetal, it's going to be an ionic bond. This is always true for this class, even if the numbers work out differently. So, for example, this partially positive or this fully positive thing, this might be potassium, and this in green might be chlorine, for example. Potassium is a metal. It's over here in our alkali metals, right? So it's definitely a metal. And then chlorine, being a halogen, is definitely a nonmetal. So just based on their identities as a metal or a nonmetal, since they're together, we can figure out that it's ionic. It's an ionic compound. It's an ionic bond. Okay, so ionic compounds have ionic bonds. Any bond between two atoms of the same element is nonpolar. Waving my Apple Pencil back and forth to hypnotize you into remembering that. Ionic compounds have ionic bonds. Memorize those, please. If there's an intermediate electronegativity, this is what we were looking at kind of as we introduced the idea of electronegativity. So somewhere in between, somewhere between perfectly matched and completely lopsided, there's this exciting realm, and that's the intermediate category. So this is where we get our polar covalent bonds, and polar covalent bonds are common between two nonmetals. It's not always going to happen, but that's typically where we're going to see it, is between two nonmetals. So for example, our hydrogen and our chlorine here. Hydrogen typically classified as a nonmetal, chlorine always classified as a nonmetal. And if these sort of like fuzzy definitions don't suit you, we also have a numbers version. So ultimately, the degree of polarity is continuous. So you've got like pure covalent where they're exactly perfectly evenly matched. And then it kind of ramps up in polarity until you get to the ionic side of things. And then it's basically the electrons transferred. And we've got some sort of arbitrary cutoffs for our difference in electronegativity. So under around 0.4 is nonpolar. We're talking about the difference in electronegativity. I'll write out electronegativity here. So our difference in electronegativity. So you take the value for one of the atoms, you take the value for the other atom, looking it up on your yellow sheet or being provided it, and then you figure out what's that difference and where does it lie on our table. If it's under 0.4 or it's about 0.4, nonpolar. There might be a little bit of pull one way or the other, but it's not that big of a deal. It's not that big of a difference. Anywhere from that 0.4 to 2 is going to be polar. Anything above 2 is ionic. So for our chlorine bonded to chlorine, our electronegativity value, our difference, is subtract one from the other. They're exactly the same. And so our difference would be 0. For our polar case here in the middle, our hydrogen has a value of 2.1. I believe chlorine has a value of 3.5. So we do 3.5 minus 2.1 we get a value of 1.4, which falls into this range of 0.5 to 2.0. So we would call it a polar bond based on that. For our ionic part, if we're doing potassium and chlorine, our difference in electronegativity is going to be that 3.5 from what I think is for chlorine, and then what's the value for potassium? 0.8? 0.8. Perfect. So 3.5 minus 0.8, which is going to be 2.7. That's above 2, and so we would say that it's ionic. We could also say that it's ionic, though, based on it being a metal and a nonmetal. So there's a couple of ways to do the identification. You don't always need the electronegativity values. You never need to have any of them memorized except for 4 for fluorine. That's the one that you should know. Questions about any of this so far? Because we're going to do some more building. Okay. Exercise. We love exercise. Classifying bonds. Classify these bonds as pure covalent, polar covalent, or ionic. If you don't have the values, go ahead and write those in for the electronegativities for you. Oh, chlorine's 3.0. That's okay. Okay. Looking at these bonds, trying to identify them as pure covalent, which is nonpolar, polar covalent, or ionic. Looking at nitrogen bonded to nitrogen, it's the same thing. They're going to have the same electronegativity values no matter what they are. So this is going to be nonpolar. HR asked us to find the difference between these two pictures. It's the same thing. If we wanted to do a little bit of easy math, our difference in electronegativity, 3 minus 3, which gives us a value of 0, and 0 is less than 0.4, so it's nonpolar. Looking at Rb and Cl, what kind of thing is Rb? How would we classify it? It's a metal. How would we classify Cl? It is a nonmetal, and so this is going to be ionic, metal, and nonmetal. Also, the difference in electronegativity, 3.0 minus 0.8, which is 2.2. That's above our threshold of 2, and so it's an ionic bond.
Do you always subtract the larger number? Like, the larger...
Yes, you don't have to do it that way, but if you get a negative number, make it positive. Okay, and then we've got P and O, and we will have to figure out what it is. So let's look at the electronegativity difference. It's 3.5 minus 2.1. That gives us a value of 1.4. So it is polar covalent. because it's between 0.4 and 2.0. Follow-up question. Which of the two elements is going to have more of the electron density, or is going to have the electrons closer to it? Oxygen. Oxygen is hoarding / pulling the electrons. Questions about those? Okay. Building. Having polar bonds does not mean that the entire molecule is polar. So you can have polar bonds and have a nonpolar molecule. So molecules, we've been looking at just one bond. Molecules as a whole can also be polar, nonpolar, ionic. So what happens in a polar molecule is that a polar molecule has a net or overall dipole moment. So if we look at the molecule as a whole, one part of the molecule will have a partial positive, and then another part is going to have a partial negative charge. So it's sort of like the bond, it's spread out across the entire molecule. So for these, the polar bonds are going to add together. The partial positive parts point in the same direction, roughly. And the same is true for the partial negative. If we have a diatomic molecule, meaning we've just got two atoms in it, like HCl or N2, if it has a polar bond, it is a polar molecule because there's no opportunity for that pull to be canceled out by something else. So that's a good maxim or a good rule. In molecules with more than two atoms, two or more polar bonds may cancel one another. So this is where knowing our shapes can come into play. For example, carbon dioxide has two polar bonds between each of the oxygens on the outside, represented in red, and our carbon in the middle. So our difference in electronegativity is 1.0, since carbon's a 2.5, oxygen's a 3.5. However, it's got the linear geometry. And so the oxygens are on either side, and they're both pulling, they've got the higher number, they're both pulling the electrons away from the carbon, but they're on opposite sides. So in my mind, I'm thinking of two really big people on the outside, two big twins on the outside, and they've each got one arm of a much smaller person in between them, and their like legs are up off the ground and they're like kicking, but they're not in pain. But they're getting held up in between these two big people. Because the two big people on either side are pulling with the same strength, and the little person is stuck, the smaller person is stuck in between them, right? The big people aren't moving one way or the other because they're both pulling with equal force from the outsides. So because it has a linear geometry and these poles are opposite and equal, they cancel out. So the opposite and equal poles cancel. So there's no net dipole. And the way that these arrows work is that the arrow points in the negative direction, and the plus side, the little plus part, is the positive side. So this is saying that the oxygens are pulling to either direction, both directions. Questions about that? So that's our simplest shape. But remember, we have other shapes. We've got 4 other shapes. So this molecule is nonpolar because the poles cancel each other out. we can represent polar bonds with arrows or scary vectors that point in the direction of the negative pole and have a plus sign at the positive pole. So this little secret plus sign in there that's not so secret. If the arrows or the vectors point in exactly opposite directions, then the dipole moments cancel. The way that we would do vectors is you would take your arrows, if they're not pointed like directly along an axis, if we like think about plotting this, let's draw it. If we plot this, there's our x, there's our y, and we've got an arrow that's pointing up and to the right. What we would do to make this into vectors is we would separate it out into x component and y component. So we've got the x force or vector, and we've got the y force slash vector. If you're scared, don't worry, we don't need to actually do vectors, but just pointing it out, this is an approach that you can do. Generally, I think it's a little bit too complicated for what we're doing. But that's the way that you would separate an arrow into its component parts, its vectors. It's extra fun if we're doing it in 3 dimensions. So, for example, water. For polar molecules, water contains 2 polar bonds between our oxygen in the middle and our hydrogens on the outside. Water has the bent shape because our oxygen has lone pairs on it. And so the shape that it gets is bent. And so these arrows are not pointing and completely canceling each other out. So if we looked at this with vectors, just to show you in 2 dimensions that it works, right, we've got these up components, the vertical components, we've got the side-to-side components. You can see probably these side-to-side components are pointing in opposite directions and they're the same size. So those cancel out. However, wrong button. Okay, one sec. However, these vertical arrows are pointing in the same direction, so they add up. And so the net force would be putting those 2 little arrows on top of each other. They didn't cancel out completely, so we've got a pull up in the way that we've drawn it here. We'd have these little plus signs. Because they didn't completely cancel out and we've got polar bonds, the molecule is polar. Questions? Okay, so these are some of the common cases that we might encounter of where we can get a polar or nonpolar. So we've got our polar examples up here on the top. We've got a diatomic molecule. So we've just got 2 atoms. We've got a polar bond. There's nothing to cancel it out. We don't have something pulling in the opposite direction. And so the molecule is polar because that dipole is uncanceled out. We've got this trigonopyramidal shape. The trigonopyramidal shape, all of these hydrogens are getting bullied by the nitrogen in the middle. And if we were to like flatten it out, it would look kind of like this BF3. If we were doing a top-down look, all the arrows canceling out pointing towards the nitrogen would cancel out. But because it's pyramidal, this one, right? That's better. this way, right, there's going to be a net additive force. All the components, if we're looking at this BF3, would be coming out of the board. So they don't completely cancel out. And for this CH3Cl, we've got this polar bond between the carbon and the chlorine and nonpolar bonds between the carbon and the hydrogen. So there's, again, nothing to cancel out that pole. This would be a tetrahedral shape. For nonpolar things, we've got a trigonal planar shape. If you're scared, just bear with me. And we've got a tetrahedral shape. And for our trigonal planar shape, all the bonds are the same. For our tetrahedral shape, all the bonds are the same. And these are as spread out as they can be because of the way that valence shell electron pair repulsion theory works. Right? If we get three things, they're completely spread out. And so you could think of if I was getting pulled by my hands and my feet, the way that I'm standing in the Y shape with my feet together, right? It would probably hurt me, because why are three people pulling on me? But also the forces would cancel out, because they're equal pulls. And the same thing for the tetrahedral shape, just in four directions. We don't want to map the vectors for these because it's gross. Okay, 2 more slides, and then we'll stop for the day. So to determine whether a molecule is polar, it has to have polar bonds. Must have polar bonds. At least one polar bond must be present, otherwise it's not going to be polar. So if you do your check, if you're looking at all your different pairings on your Lewis structure, you don't find any polar bonds, congratulations, it cannot be polar. You can just stop there. No polar bonds, no polar molecule. And then you can determine if the polar bonds add together to form a net dipole moment. So you can use our shape theory, pose it out to determine the molecular geometry, and then think about, is it symmetrical? And that might be scary. There's a shortcut, and that's the last slide. I wanted to leave you with some relief. Okay, so this is sometimes called Mrs. K's alternate method for determining molecular polarity. I prefer the title nonpolar express, since it's our fast track for coming up with whether something's nonpolar. So we want to look at the Lewis structure for the molecule. So we still have to do Lewis structures. It will be nonpolar if both of these things are true. That's why it's the nonpolar express. So if both of these are true, there's no lone pairs on the central atom, and the atoms are all the same. The atoms bonded to the central atom are all the same. If there's no lone pairs, it'll be linear or trigonal planar or tetrahedral for its overall shape. And those three shapes are all with the groups as spread out as they can possibly be. And so if they're all the same bonds, the same bond strength, then when they're pulling or pulling to the inside, whatever that force is going to cancel out because they're all perfectly spread out. So if you went through and did all the vectors and you scared yourself, wait 2 weeks because Halloween. If you scared yourself with all the vectors, right, you would find out that they completely cancel out. So this will often be the fast track for figuring out. If either is false and we have a polar bond, then it's polar. Any questions? Okay, then we'll stop there.